So in this video, what I want to do is to use the mathematical technique of proof by induction in the context of calculating a definite integral. And what I want to show is that the integral from 0 to pi by 2 of sine of theta raised to the power of 2n integrated with respect to theta is 2n factorial times pi divided by n factorial squared and also divided by 2 to the power of 2n plus 1, and this is for n a natural number. And the technique that we're going to use is proof by induction, so there are going to be 3 steps. We are first going to check it works for the simplest value of n. We are then going to assume it works for an arbitrary value, and then we are going to demonstrate that with that assumption we can show it works for the next value of our label, which here is n. So let's start by checking that this holds for n equal 0. And to do this, I'm going to introduce a little bit of notation back here. I'm going to label our integral, our statement, that this is equal to this. I'm going to label it, and I'm going to say that I sub n is equal to this integral, and that it's equal to this. So for n is 0, what we have is I0 is the integral from 0 to pi over 2. Sine to the twice 0 is 0, so sine to the 0 of theta with respect to theta. And that's the integral from 0 to pi over 2 of 1 with respect to theta. And that integral is theta between 0 and pi over 2. So it is pi over 2 minus 0, or just pi over 2. So let's compare that with the claim. The claim is that I0 is equal to 2 times 0 factorial, so that's 0 factorial, times pi, divided by 0 factorial squared, so that's 0 factorial squared, and then 2 to the 0 plus 1, so 2 to the 1 is also on the bottom, so it's 2 to the 1, or just 2. Now 0 factorial is 1, so on the top we have pi, on the bottom we have 1 squared times 2, so that is pi over 2. So our calculated integral is equal to our claimed result for the integral. So we see the claim, the thing we are trying to prove, works for n equals 0. And if it hadn't, we could have stopped at this stage because our statement would have been wrong. A single counterexample shows that there would be something wrong with it. So what we're going to do on the next slide is return to this, assume it's true, replacing n here by k. This is, after all, a statement. This is equal to that for infinitely many values of the label n. And we're going to say for an arbitrary value, which we'll call k, we're going to assume it's true and then try to check that it is true, or try to demonstrate that it is true for the next value of the label. So let's look at this on the next slide. So here we have our assumption. For n replaced by an arbitrary label k, we are assuming that this is true. So for some particular value we assume it is true. And now what we want to do is to show that our claim is correct, that our claim holds for the next value of our label, that's going to be k plus 1. So ik plus 1, the thing we want to prove, is the integral from 0 to pi over 2, sine of 2 times k plus 1, so that's 2k plus 2 of theta with respect to theta. That's what the integral is, replacing the label by k plus 1. And we want to show that this is 2 times k plus 1, so that's 2k plus 2 factorial here. Pi is the same always, so we'll just put pi there. And on the bottom, where we had k factorial squared, we have k plus 1 factorial all squared, and then we have 2 to the 2 times, and now k is replaced by k plus 1, so it's 2k plus 2 plus this 1, so we have 2 to the 2k plus 3. And this is the result we want to show, and to do it, to use proof by induction, we need to use our assumption. So in this context, what we want to do is to look at this integral and try to somehow manipulate it into a form where we can substitute our assumption in, and then we hope in that way to show that our integral is equal to this. And to do that, to have an integral of sine to the power of 2k appearing, I think it is quite natural to factorize this sine to the power of 2k plus 2. And the question is, what should we pull out of this? If we were to say multiply this by 1 and then integrate the 1, we would generate a theta, and that would take us outside of this class of integrals, so that would be no use to us at all. So we're going to pull one of these powers of sine out. You could explore trying to pull 2 powers of sine out, and that I think will also just take you outside of this class of integrals, and it will give you an equation which is true but not helpful for proving this. So what we want to do is to write our integral as the integral from 0 to pi over 2 sine to the 2k plus 1 of theta times sine of theta integrated with respect to theta. And now we are going to use integration by parts. So the term that we are going to integrate is this term. After all, if we could integrate this straightforwardly, we would just integrate it up here and there wouldn't be any problem. So this is the term we want to integrate. So I'm going to say that this is v prime, and this factor here, this structure, is the one that we're going to differentiate, so I'm going to call that u. And the formula that we are going to use is the integration by parts formula, that the integral of u v prime with respect to our variable here theta is uv minus the integral of u prime v with respect to our variable. So this is the integration by parts formula. This is what we are going to use it on, and we can now work out what u prime, the derivative of u, and what v are. So u prime is the derivative of this. We pull a factor of 2k plus 1 in front, reduce the power to 2k, and from the chain rule multiply by a derivative of sine, which gives us cosine. So what we have is that this gives us 2k plus 1 sine to the 2k of theta cosine of theta, and that follows from the chain rule. And v is just the integral of sine of theta, and that is minus cosine of theta. Differentiate minus cosine theta, you get sine of theta. So therefore, the integral that we are trying to calculate is, well, it's u times v. U is here, v is minus cos theta, so it is minus, I'll put the minus sign in front, cosine of theta, sine to the 2k plus 1 of theta, and this is all evaluated between 0 and pi over 2. And then from the next part of the integration by parts formula, we have minus the factor of 2k plus 1 here, that's going to be here in the u prime. I'm going to pull it outside of the integral. So I'm going to write 2k plus 1, close brackets, integral 0 to pi over 2. And now we have sine to the 2k of theta times cosine of theta. So that's sine to the 2k of theta times cosine of theta. And now we have to multiply by v, and v is minus cos theta. So the extra power of cos theta makes this cos squared theta, and the additional minus sign I will put in front of all of this and turn this into a plus. So that minus sign came from the integration by parts formula, and this additional minus sign makes this plus. So I just make it plus now. And this is integrated with respect to theta. Now, the good news is that this entire term is going to vanish. At pi over 2, we have a factor here of the cosine of pi over 2, and the cosine of pi over 2 is 0. At the bottom, we have sine to the power of something positive of 0. So at the lower limit, sine of 0 is also 0, so this factor will vanish as well. So this vanishes at the upper limit, and at the lower limit it is completely 0. So let's just immediately say that this goes to 0. So now what we want to do is we have the integral we're trying to calculate, and we now have this integral, and this might look for a moment as though we were going away from our class of integrals of even powers of the sine function, but we have cos squared theta, and we know we can rewrite cos squared theta as 1 minus sine squared theta. So what we have is our integral with the label k plus 1 is equal to 2k plus 1 times the integral from 0 to pi over 2 sine to the 2k of theta times 1 minus sine squared theta, all integrated with respect to theta. And now what we have is this integral has become two integrals. It is the integral, they're both from 0 to pi over 2. It is the integral of sine to the 2k of theta, and that makes us very happy because that was our assumption. We can use this, minus the integral of sine to the 2k plus 2 when we multiply this and this together. But the integral of sine to the 2k plus 2 is the integral we are trying to calculate. So what we can say is that I sub k plus 1, so this is the integral we're trying to calculate, is 2k plus 1 times, and now we have the integral from our assumption, which we're calling I sub k, and then we have minus, because of this minus sign here, I sub k plus 1. So again, just to emphasize it, this is two integrals. The first part is the integral that we've called I sub k, that was our assumption, and the second one is the integral of sine to the 2k plus 2 with a minus sign in front, and that is the integral we're trying to calculate. So what we have generated on this slide is an equation linking the integral we are trying to calculate here and here and our assumption. So what we have to do now is to solve this equation to find the integral that we're trying to calculate, insert our assumption for this, and show that indeed we obtain this result. So I'm going to do that on the next slide. So on the previous slide we just obtained this equation linking the integral that we're trying to calculate here and here and the integral that we have made an assumption about. So we're going to take the integral that we're trying to calculate, all of those terms, over to the left hand side, and what we have then is that I sub k plus 1 multiplied by 1, that's the term here, and then we're bringing these over, so we're adding it to this side, sorry, adding it to both sides, so it's plus 2k plus 1 of it is equal to 2k plus 1 multiplying the integral that we've made the assumption about. And terms in the brackets here are 2k plus 2 overall, so this gives us the result that the integral that we are trying to calculate times 2k plus 2 is equal to this, so let's divide both sides by 2k plus 2 and we get 2k plus 1 on the top over 2k plus 2 times ik. So now we have been able to use integration by parts, and we've related the integral that we're trying to calculate to the integral we've made an assumption about. So let's use our assumption. So if you just look back at the previous slide, or whatever you may have written down while we've been going through the video, what you will see is that we can now write 2k plus 1 over 2k plus 2, that is just this factor here, times the form of ik, and ik is 2k factorial times pi all over k factorial squared, and we have 2 to the 2k plus 1. And I think it's often helpful in such circumstances just to remember what we're trying to show. So we are trying to show that ik plus 1 is 2 times k plus 1 all in brackets factorial times pi over k plus 1 factorial all squared, and 2 to the 2 brackets k plus 1 close brackets plus 1. So let's just expand that out a little bit. This is 2k plus 2 factorial times pi over k plus 1 factorial all squared, and it is 2 to the 2k plus 2 plus 1, so it's 2k plus 3. So what we want to show is that this is equal to that, and then we will have obtained our result. So from this equation we have k plus 1, the integral of the label k plus 1, is, so here we are multiplying 2k plus 1 by 2k factorial, and that is 2k plus 1 factorial, in the same way that 5 times 4 factorial is 5 factorial. So 2k plus 1 times 2k factorial just increases the factorial to 2k plus 1 factorial. Pi is an overall factor that just sits there, and on the bottom we have got 2k plus 2, so that is 2 times k plus 1. So the 2 can be multiplied into here to increase the power by 1. So I'm taking the overall factor of 2 here into here. So I have 2 to the 2k plus 2. And on the bottom I am left with a k plus 1 factor, and that can be multiplied into one of the 2k factorials here to give a k plus 1 factorial, and the other of the k factorials here, this is k factorial times k factorial, just sits there unchanged. So let's look at what we have and what we're trying to show. We would like another power of 2 here on the bottom, so that we have 2 to the 2k plus 3. And if we multiply by 2 on the bottom, we have to multiply by 2 on the top. We would like to have k plus 1 factorial here, and to get that we have to multiply in the bottom by k plus 1. K plus 1 times k factorial is k plus 1 factorial. But that means we've got to multiply in the top by k plus 1 as well. So what we get is there is a factor of 2, and there is a k plus 1, and then we have a 2k plus 1 factorial times pi, the last two terms just being these. And on the bottom we have k plus 1 factorial times k plus 1 factorial. So the k plus 1 I've multiplied top and bottom by. On the top it's there, and on the bottom I've used it here to turn this into k plus 1 factorial, and the factor of 2 on the top and bottom, the one on the bottom increases this power, and I have 2 to the 2k plus 3. And now we just notice that 2 times k plus 1 is 2k plus 2, and 2k plus 2 times 2k plus 1 factorial is 2k plus 2 factorial. So therefore I, with the label k plus 1, is 2k plus 2 factorial times pi over k plus 1 factorial all squared, and 2 to the 2k plus 3. And this is as we needed to show. So what we've done is we have taken our integral, shown it works for when the label has value 0. We've then assumed that it is true for some arbitrary value that we've called k, and then we've proven that if it is true for the label k, it is true for the next value of the label k plus 1. So since it holds for I is 0, we've checked that, it must work for n is 1. Since it works for I1, it must then work for I2. If it works for I2, it must work for I3, and so on for all values of n. So since it works, our identity holds for n equals 0 by the principle of induction. Our relation is true for all n in the natural numbers. So we have in this video proved infinitely many relations for all the infinitely different possible values of the label n. With that, I will stop this video.